that is nothing but delta M into C square, right? And delta M is what? Mass defect. And if I write that expression for mass defect, it's nothing but Z times MP plus N times Mn minus M NuCl. Okay, where NuCl is the actual nuclear mass, right? And then you have C square, right? This is the expression, right? So this will be the binding energy. Now you see here you have a what? This is your nuclear mass, right? There's no atomic mass here. It's the nuclear mass. Now what I'll do, I'll add ZME, electronic mass of Z number of electronic mass I'm adding, right? And then I'm writing NMN. Can you please mute your mic? Can you please mute your mic? So I've added ZME. Then I have to subtract that also. And you already have MNuCl. So I can write like this. Right? In fact, from this two term, I can get Z common. Now, when you have a nuclear mass and you are adding mass of Z number of electron, what will happen? आपके पास nuclear mass है and you are adding the mass of n number of electrons. And what will happen? This will be converted to atomic mass, right? When you have a, so atomic mass is nothing but nuclear mass plus electronic mass, right? You have a in your whole atom, you have a nucleus and you have a electron. How many electrons are there? You have a Z number of electron. So if you have a nuclear mass, then you are adding the mass of Z number of electrons. So this whole quantity is nothing but mass of atom. And in fact, if you have a electronic mass and you are adding protonic mass, so what will happen to this? This I can write the mass of a hydrogen atom. Because in hydrogen, if you have a structure like this, it has only on proton and on electron, right? So mass of the proton with electron will provide you mass of hydrogen atom, this atom. So in fact, binding energy I can express like this also. ZMH plus NMN minus mass of atom. So that's why we have used this symbol. This symbol is representing nuclear mass, and this symbol is representing your atomic mass. So you can express your binding energy in terms of nuclear mass. Then this at this scenario you will have ZMP here. However, if you want to convert it into atomic mass, or if you want to write it in atomic mass, you have to write this as a ZMH. Is this clear? Tell me yes or no.
Yes, sir.
Yes, sir.
Okay. So start a discussion on binding energy per nucleon carbon. right? Because the stability or relative stability basically investigated from binding energy per nucleon value, right? When a nucleon is having higher binding energy per nucleon, it means that will be more stable. And among all nuclei, the highest binding energy per nucleon is having which nuclei? That is your iron, right? So among all nuclei, iron will be the most stable nuclei. Okay. Iron will be the most stable nuclei. Okay. Okay. And also you have noticed that for low mass number, actually binding energy per nucleon depends upon mass number. For low mass number, the binding energy actually less, especially when mass number less than 30. But except is there, exceptional case is there, like you have a helium, carbon, and oxygen. They have low mass, however, due to their paired number of pairing of neutron and proton, they are actually having higher binding energy per nucleon, which implies they're actually stable. And in between mass number 30 to 120, they are having higher binding energy per nucleon. So they are basically relatively more stable. However, when you are increasing that mass number, like especially when it is greater than 120, then there's a Coulomb repulsive force. It's actually dominated in the system. As a result, there's a decrement in the binding energy. So low mass side, due to the low binding energy, they will fuse together, and they will make relatively heavy nuclei. Okay, and we have observed during fusion, we will have release of energy. So when you have to keep in mind, whenever you have a reaction, in a reaction, if the binding energy of the product is greater than the binding energy of reactant, I mean total binding energy of product, if it is greater than the binding energy of reactant, it means in that reaction there will be release of energy. So yesterday we have noticed when you have a fusion process, there will be higher binding energy of the product. As a result, or therefore, in a fusion process, there will be release of energy. Same is true for fission process. But fusion is happening for low mass and fission is happening for heavy mass. In fission process also, the product is having a higher binding energy as compared to reactant. As a result, there will be release in energy in fission process also. Is this statement clear to all?
सर एंड में आपने जो बताया ना वो सिर्फ एक बार फ्यूजन का सिर्फ एक बार बताइए
हाँ जी, fusion के लिए yesterday I have noticed there is a release of energy. Why? Because the product is having higher binding energy compared to reactant, right? The same is true for fission process also. When you have a fission process, it's basically happening for heavy nuclei, but during fission process also, the product is having higher binding energy compared to reactant. Okay, as a result, there will be a release of energy in fission process also. And you can mention also in fission process, the amount of energy per fission process is actually high. That energy is around, actually I'll go in details in fission and fusion process. That's why I'm not taking much time here, because you have to understand that how that star is releasing energy, or any other fission process also. The star, there you have a fusion process, right? And in nuclear reactor you have a fission process. So this will understand in details, or will study in details at the end of nuclear physics. But right now we have to keep in mind that fusion process is happening because of low binding energy per nucleon. Same is true for fission also. And in fission and fusion, in both cases, the binding energy of the product is higher than reactant. As a result, there will be release of energy. Especially if I talk about that fission process, the release of energy is not small. That release of energy per fission process is around 200 mega electron volt. Okay. Now, this was the binding energy about, I mean, that stability curve. Now there is some experimental fact. There's some experimental fact. Some experimental fact about nuclear stability. So first fact is evenness and oddness. Evenness and oddness of proton and neutron. So a Z representing number of proton, N presenting the number of neutron, and you have a number of stable nuclei. Number of stable nuclei. Okay. When that both proton number and neutron number is even, then what you are expecting? Tell me. Number of stable nuclei ज़्यादा होगी या कम होगी?
ज्यादा होगी सर.
Any idea number? Of course, it will be large because they will have a higher binding energy per nucleon, and that number is 166. But if the number of proton is even and neutron is odd in a nucleus, and then number of stable nuclei will be not that much, but it will be around 57. There are basically 57 stable nuclei exist which are having even number of proton and odd number of neutron. Any other possibilities?
Odd even.
Odd even. When you have odd number of proton and even number of neutron, then what will happen? What will happen? This number is reducing to 53.
Odd and odd also.
Exactly. So you have odd combination. You have a odd combination, and that number of stable nuclei for odd combination is only 4. Okay. And so obvious, right? When you have even combination, all nuclei are paired. So obviously it is expect that in paired case, the number of stable nuclei will be large because binding energy per nucleon will be large for paired neutrons and protons. But when you have a even odd combination like Z even N odd, that number is reduces from 160 to only 57. And then you have a 53, and odd combination, the number of stable nuclei is only 4. Another important fact about nuclear stability is n by z ratio. N by z ratio. N by z ratio. So you have a जी
उसके पहले जो हमने देखा है ना, उसके पीछे रीजन कुछ है क्या? मतलब z even and odd होगा तो 57, मतलब exactly not number, there is more in this case compared to odd even.
हाँ, जब आपका z इवन है तो नंबर मोर, और जब आपका n इवन नंबर लेस, ये कहना चाह रहे हो ना? You are trying to ask me like when you have a even number of proton but odd number of neutron, then you have 57. However, when you are going z odd but n even, it is 53, right? You are saying like this, right?
Yes, sir.
Why there is a reduction in number, right? Are you asking like this?
Yes, sir. Yes, sir.
Yes. It's so obvious because you know when you have a proton is unpaired, right? When proton is unpaired, tell me whether it is easy to remove proton or neutron from nucleus. जब आपका दोनों प्रोटॉन अनपेयर्ड, दोनों प्रोटॉन पेयर्ड है, पेयर्ड से निकलना बहुत डिफिकल्ट है, ठीक है? सो प्रोटॉन के पास क्या है? दो फोर्स है, एक तो आपका कूलम्ब फोर्स है रिपल्सिव, और न्यूक्लियर फोर्स है। दोनों जब पेयर्ड है तो दोनों बहुत स्ट्रांगली बाउंड है, दोनों प्रोटॉन, वेरी हार्ड टू रिमूव, है ना? तो जब आपका प्रोटॉन पेयर्ड है, प्रोटॉन को रिमूव करना भी डिफिकल्ट है। और न्यूट्रॉन क्या है? न्यूट्रॉन ऑड है, हाउएवर न्यूट्रॉन आर स्ट्रांगली कनेक्टेड टू न्यूक्लियर फोर्स। प्रोटॉन के पास तो एक रिपल्सिव फोर्स होती है ना। व्हेन प्रोटॉन आर कनेक्टेड, दे आर पेयर्ड, इट इज वेरी डिफिकल्ट टू रिमूव प्रोटॉन। यू हैव ए ऑड नंबर ऑफ न्यूट्रॉन, सो न्यूट्रॉन को निकालना, न्यूट्रॉन के पास क्या है? न्यूक्लियर फोर्स है ओनली। तो जब आपका ऑड नंबर या अनपेयर्ड न्यूट्रॉन है, उसको रिमूव करने के लिए जितना एनर्जी चाहिए। आप दूसरा केस में आ जाओ, जब आपके पास ऑड नंबर ऑफ प्रोटॉन है, जो अनपेयर्ड प्रोटॉन है एक, और एक आपका दूसरा केस में अनपेयर्ड न्यूट्रॉन है, किसको रिमूव करना इजी है? पहला केस में क्या है? आपका अनपेयर्ड न्यूट्रॉन है, और दूसरा केस में क्या है? अनपेयर्ड प्रोटॉन है, राइट? अनपेयर्ड प्रोटॉन मतलब आपका जब पहला केस क्या है? जब आपका जेड इवन और एन ऑड है। दूसरा केस क्या है आपके पास? जेड ऑड एन इवन। तो जब पहला केस में एन ऑड है, तो अनपेयर्ड न्यूट्रॉन को रिमूव करना इजी है या अनपेयर्ड प्रोटॉन को रिमूव करना इजी है? न्यूट्रॉन को।
सो जो अनपेयर्ड होगा,
नहीं, दोनों, पहले केस में भी, पहले केस में अनपेयर्ड न्यूट्रॉन है, दूसरा केस में क्या है आपके पास? अनपेयर्ड प्रोटॉन है। न्यूट्रॉन के पास न्यूक्लियर फोर्स है, दैट इज अट्रैक्टिव, तो इट इज डिफिकल्ट टू रिमूव ए न्यूट्रॉन फ्रॉम न्यूक्लियस। प्रोटॉन के पास क्या है? एक तो न्यूक्लियर फोर्स है, दूसरा क्या है? कूलम्बिक रिपल्सिव फोर्स है ना। तो जब आपका प्रोटॉन अनपेयर्ड है, प्रोटॉन को रिमूव करना, जो अनपेयर्ड प्रोटॉन है उसको रिमूव करना इजी है ना? और न्यूट्रॉन जो है उनको रिमूव करना टफ है, बिकॉज न्यूट्रॉन के पास ओनली न्यूक्लियर फोर्स है, प्रोटॉन के पास क्या है? कूलम्बिक फोर्स भी है और न्यूक्लियर फोर्स भी है। हाँ, तो इसीलिए जब आपका अनपेयर्ड प्रोटॉन है, इट मींस दैट अनपेयर्ड प्रोटॉन कैन इजीली डिके। अनपेयर्ड प्रोटॉन कैन इजीली डिके। आई मीन यू हैव ए टू केस, आई मस्ट से, व्हेन यू हैव ए number of neutron odd, it will have large binding energy as compared to second case, क्योंकि second केस में क्या है? आपका अनपेयर्ड प्रोटॉन है जो कूलम्ब रिपल्सिव फोर्स सफर कर रहे हैं, and due to Coulomb repulsive force, the first case will have higher binding energy as compared to odd proton वाला केस, है ना? इसीलिए आपका जो आपका even Z with odd n will have higher binding energy, so they are expecting that they will have number or stable nuclei number will be high. Are you satisfying, or I have to explain more?
Clear, sir.
Good.
Clear.
Now another aspect from that experimental observation, that is n by z ratio. N by z ratio. So if I plot z versus n, then stable nuclei with low mass number will follow. Please listening to me. The stable low mass number nuclei will follow n equals to z line. Stable low mass number, you can mention that sentence also. Stable low mass number nucleus will follow n equals to z lines. However, if you increase the mass number beyond 40, stable nuclei will not follow n equals to z line, but it will follow this case. Suppose this is the hypothetical line, like n equals to z case. But stable nuclei will not follow n equals to z line. It will only follow, that's n equals to z line, यहाँ पे आप dash 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 दे दो, up to calcium 2040. तो इस लाइन की तरफ आप जा रहे हो, क्या हो रहा है एक्चुअली? मास नंबर बढ़ रहा है. When you are going this line, both n and z are increasing. It means mass number is increasing, right? Are you getting what I'm saying? When you are following this line, you are going through this line, both z and n increasing. यहाँ से जैसे यहाँ गया तो आपका n भी बढ़ जाएगा, z भी बढ़ जाएगा. इसका मतलब when you are going forward to this line, both n and z increasing, so mass number is increasing. And stable nuclei will follow n equals to z line. Stable nuclei will follow n equals to z line up to mass number कितना? Mass number कितना? Tell me.
40.
So low mass number nuclei will follow n equals to z line up to mass number 40. Here you have a no problem. However, when you are increasing that mass number beyond 40, stable nuclei will not follow n equals to z line. Rather, यहाँ पे n equals to n क्या होगी? कम होगी या ज्यादा होगी? Of course.
ज्यादा होगी सर.
Of course.
ज्यादा होगी.
So stable nucleus with mass number greater than 40 will have a higher number of neutron greater than proton. And reason behind that is what? Because when you are increasing that proton number, there is a increment of Coulomb repulsive force. And this is actually disruptive force that will decrease the binding energy. है ना? जैसे जैसे आपका सिस्टम में proton number बढ़ रहा है, what is happening? There is a disruptive force that is increasing, or Coulomb force is increasing, that is actually decreasing the binding energy. But नेचर ने ऐसा नहीं किया. नेचर ने क्या किया? नंबर ऑफ न्यूट्रॉन को बढ़ाया. और नंबर ऑफ न्यूट्रॉन बढ़ने से क्या फायदा हुई है? जैसे जैसे आपका नंबर ऑफ न्यूट्रॉन बढ़ा है, आई मीन both are increasing. When you are increasing the mass number from 40, both n and z are increasing, but rate of increment of n is large as compared to z. क्योंकि z अगर बढ़ते तो फिर क्या होता? Coulomb repulsive force बढ़ते, और Coulomb repulsive force बढ़ते मतलब क्या होता? बाइंडिंग एनर्जी कम हो जाता. बाइंडिंग एनर्जी कम मतलब क्या है? न्यूक्लियस अनस्टेबल है. हाउएवर इंक्रीमेंट ऑफ न्यूट्रॉन का फायदा क्या है? जैसे जैसे आपका न्यूट्रॉन नंबर बढ़ रहा है, there is an increment of nuclear force. क्योंकि nuclear force depends upon what? Nucleon, right? Nuclear force depends upon nucleons. तो जैसे जैसे n बढ़ रहा है सिस्टम में, there is an increment of nuclear force. As a result, there is an increment of binding energy, and that is basically stabilize that nucleus. तो नेचर ने इसको कैसे किया? कैसे अपोज किया n equals to z को? हाँ, ऐसे बढ़ता फिर आपका क्या हो जाता? Coulomb repulsive force बढ़ता. There is decrement of binding energy due to Coulomb repulsive force, and their system will be unstable. So नेचर ने इसको अपोज इसी वजह में किया, नंबर ऑफ न्यूट्रॉन को बढ़ाया, ताकि नंबर ऑफ न्यूट्रॉन बढ़ा मतलब योर न्यूक्लियर फोर्स इज इंक्रीजिंग, or nuclear force increasing मतलब binding energy is increasing. So when there is an increment in binding energy, then your nucleus will be stable. However, there are few nucleus is observed to be here. कुछ न्यूक्लियाई इधर भी मिलता है, कुछ आपका इधर भी मिलता है. There are some nuclei on the left hand side of stability curve and some nuclei on the right hand side of stability curve. So they are actually not stable. So जो आपका left hand side में है, how will they will achieve stability? So first of all, जो nuclei आपका left side में है, the nuclei that is lying on the left hand side, they have a higher number of neutron than the required value. मतलब स्टेबिलिटी होने के लिए जितना नंबर ऑफ न्यूट्रॉन चाहिए, लेफ्ट साइड में जो आपका न्यूक्लियर है इनके पास उससे ज्यादा न्यूट्रॉन है. लेफ्ट साइड में जो न्यूक्लियर है, देखो आप चेक करो, जो लेफ्ट साइड में जो न्यूक्लियर एग्जिस्ट कर रहा है, स्टेबल होने के लिए जितना चाहिए इससे ज्यादा है इनके पास. देन व्हाट दे विल डू? एनीवन, व्हाट दे विल डू? गिव मी आंसर.
They will need these neutrons.
So they will lose this neutrons, or I can say they will convert the neutron into proton and they will achieve the stability. And how it will be possible? कैसे possible होती है? By beta minus decay. So the nuclei locating on this side, they have higher number of neutron compared to proton. So what they will do? They will undergo beta minus decay and they will lose number of neutron, and that number of neutron is basically converted to proton. तो जो लेफ्ट हैंड साइड में है उनके पास क्या है? नंबर ऑफ न्यूट्रॉन जितना चाहिए उससे ज्यादा है और नंबर ऑफ प्रोटॉन जितना चाहिए उससे कम है. So what they will do? They will convert that number of neutron. They will convert a neutron to proton by beta decay process. As you know, in beta minus decay, what used to happen? A neutron is converting to proton by the addition of beta particle with associated neutrino. And in that process, there will be no change in mass number. Just a neutron will be converted to proton.
This is green.
Haji?
No, sir.
Screen clear?
Not.
Is it clear? Not clear?
Yeah.
Everyone facing the same problem?
हाँ, बीच में blur हो रहे हैं मेरे साइड से तो.
बाकी का भी हो रहा है? Tell me.
सर आपकी आवाज भी बीच में मतलब स्लो हो जाती है.
हाँ सर.
Actually, what happened? I have forgot my system. I'm using that office system, so there may be some problem. From tomorrow it will not. हाँ जी.
ई क्या लिखा सर? ई पावर क्या ई क्या चार्ज लिखा सर उसके ऊपर? क्या
ये चार्ज होती है, मास नंबर होती है न्यूक्लियस में. ये चार्ज होती है.
नहीं सर,
इलेक्ट्रॉन है तो इलेक्ट्रॉन. हाँ जी
सर क्या समझ नहीं आ रहा सर, वो मुझे कुछ और दिखाई दे रहा है सर.
हाँ जी, देखो, न्यूट्रॉन कन्वर्टिंग टू प्रोटॉन विथ एडिशन ऑफ बीटा. बीटा पार्टिकल क्या होती है?
इलेक्ट्रॉन सर.
इलेक्ट्रॉन, राइट. तो इलेक्ट्रॉन का चार्ज कितना होती है? नीचे चार्ज है -1 और ऊपर क्या है? मास नंबर 0 विथ एडिशन ऑफ न्यूट्रिनो.
सर मुझे लगा 3 लिखा आपने, मैंने सोचा वो क्या लिख दिया.
कोई नहीं, बट टेल मी व्हाट इज द डिफरेंस बिटवीन बीटा पार्टिकल एंड इलेक्ट्रॉन? If someone asks what is the difference between beta particle and electron, tell me what will happen. What will give that answer? Anyone?
Electron is the subatomic particle. Beta particle is nothing.
So first of all, the beta particle, I told you beta particle. Beta particle मतलब क्या होती है? Beta प्लस भी हो सकती है, बीटा माइनस भी हो सकती है. बीटा प्लस मतलब क्या है? बीटा प्लस के पास चार्ज क्या है? +1 है विद 0. बीटा माइनस के पास So in the interview, they will ask you similar kind of question. What is the difference between beta particle and electron? So beta can have plus C charge or minus C charge, or electron can have only minus C charge, right? Negative charge. Second thing, that beta particle can only be found inside nucleus. Electron can be found outside of nucleus. That's it. Okay, now tell me on the other side what will happen. This side. What will happen to this side? इनके पास क्या ज्यादा है क्या कम है? The nuclei locating on the right hand side, they will have a higher number of proton than the required value, and also they have low number of neutron than the required value. If I take this neutron, इनके पास sorry this nuclei, इनके पास देखो जितना नंबर ऑफ न्यूट्रॉन प्रोटॉन होनी चाहिए उससे ज्यादा है और न्यूट्रॉन उससे कम है. Then how they will achieve that stability? Just by decaying beta plus. Beta plus में क्या होगी? There will loss of proton and will convert to neutron. यहाँ इतना न्यूट्रॉन थे और जैसे बीटा प्लस डिके करेगी, they will lose proton on the left hand side, right? And they will achieve some height. It means there will be increment of neutron and they will achieve stability. So the nuclei locating on the right hand side, they have higher number of proton than the required value, and they have lower number of neutron than the required value that is required for stability. Then what they will do? They will undergo beta plus decay. And in beta plus decay, what is to happen? The proton will convert to neutron with the addition of plus on charge particle or positron, and you will have associated neutrino. Inside nucleus, there's no problem with this decay process. Inside this nucleus, there's no problem with this decay process. However, there's a problem outside or in free space. This decay will never be possible. In free space, this decay can be possible, but in free space, this decay will never be possible. Inside nucleus, both can be possible. Outside nucleus or in free space, this can be possible, but this will never be possible. Can you tell me what is the reason behind that? Can you tell me what is the reason behind that? So for any decay or interaction, the energy should be conserved. If you notice, on the right hand side, you have massive particle. I mean, what I'm saying, the mass of this particle will be higher than this, right? This is like 939.57. This is 938.28. And you have additional mass also. So now it is not possible from low energy to high energy, right? This is at rest. Okay. So right hand side में आपका क्या है? Heavy mass है. So light mass से heavy mass decay will never be possible. Energy will not be conserved. For any decay or interaction, energy should be conserved. But here you have a light mass particle. It cannot convert to heavy mass particle because this neutron is having higher mass as compared to proton. So it will violate the energy conservation. That's why in free space this decay will not be possible. But inside nucleus, there's no problem with this decay. But this decay can be possible in both cases because neutron is having higher mass as compared to proton. So there will be no problem with energy conservation because heavy mass can decay to light mass. Because, yeah, I mean, what I'm saying, this mass should be greater than equals to the sum of the mass of this, at least. So inside nucleus, both can be possible. Outside nucleus, this will be possible because the mass of reactant is greater than the product, sum of the mass of the product. So it will not violate energy conservation, but this decay will violate energy conservation. So this decay in interview or in GATE exam, they will ask this kind of question. This decay will never be possible in free space. And this is possible. Yes.
Sir, but inside nucleus, what is happening because of which low means there is a
Because you know this particle is interacting with other particle, right? Just I'll tell you. This particle is interacting with other particle by the exchange of particle known as pi meson. So it is actually absorbing this pi particle from other nucleon. So when it is absorbing that pi particle from other nucleon, so it will have this mass and this mass also. It will always have some extra mass, and that is due to exchange phenomena. So inside nucleus, there's always exchange of some particle that is known as pi meson. So this particle is is having some exchange effect. So it is absorbing some pi particle. So it is not having not only this mass but additional sub pi meson particle mass also. इसका mass कितना होती है pi meson का? Tell me. कितनी होती है? So mass of pi particle is like 140 mega electron volt per c square. Is this clear? What I'm saying? Tell me, then I can proceed.
Inside the nucleus due to pi
inside the nucleus, this particle is absorbing some particle known as pi meson. Okay, so it is absorbing means what? It has its own mass as well as some extra mass it has, and that is due to exchange effect. है ना? So हमेशा ध्यान रखना, due to exchange effect, this nuclei or this proton is have some extra mass, and that's why this decay is possible, because you have now 140 plus 938, and this side only 939. So no problem with this decay process. Is this clear what I'm saying?
Sir.
Okay. So this is the experimental fact, and it's really interesting. You know, this in detail we are studying actually. So in future also there is no problem. Will not face any problem for nuclear physics. Okay. Now let me solve few problems that is also important for your competitive exam. Suppose you have a two nuclei. One is neon, atomic number 10, mass number 20, and nuclear mass for this nuclei is M1, and you have another nuclei called calcium, atomic number 20, mass number 40, and nuclear mass of this is M2. Okay. Now I'm giving two options, four options. Tell me which one will be the correct. The first option is the nuclear mass will be, nuclear mass of this nuclei will be sum of the mass of the proton plus sum of the mass of the neutron, and mass of this nucleus will be M2, and that will be sum of the mass of the proton plus sum of the mass of the neutron. And also M2, nuclear mass of second nucleus is 2 times M1. Second option is, it's an interesting problem, please do it carefully. Second is M1 less than 10 MP plus 10 Mn, and M2 less than 20 MP plus 20 Mn. And M2 is twice M1. Third option, M1 less than 10 MP plus 10 Mn. 10 Mn. M2 less than 20 MP plus 20 Mn. And also it is given that M2 is greater than 2 times M1. And last option is M1 less than 10 MP plus 10 Mn. M2 less than 20 MP plus 20 Mn. And M2 is less than 2 M1. Tell me which one will be the correct among these. And this kind of question you will get. And these are stable nuclei, right? Neon 10, 20, 20, 40. First of all, tell me, is this nuclei stable or not? Tell me answer, then I'll proceed. Otherwise, I'll not proceed.
Stable, sir.
Stable, sir.
They are stable, okay, no problem. So when they are stable, their mass, their actual nuclear mass will be less than their constituents. इनका constituents क्या है? 10 proton है, 10 neutron है. So of course M1 actual
Yes.
nuclear mass है, and that will be less. So this option will not be correct. Now among this will be the correct. That you have to check. Okay. Now tell me how will write that nuclear mass. If I write that mass M1, कैसे हम लिखेंगे इसको? 10 MP, right? Plus 10 Mn minus क्या लिखेंगे? क्या हम ये लिख सकते हैं कि बाइंडिंग एनर्जी पर C स्क्वायर, क्या लिख सकते हैं इसको? बताओ इसको. Because if you remember, binding energy formula was what? क्या थे binding energy आपके पास? Mass defect delta M C square. Now if you bring this C square this side, and if you write delta M, in delta M you have minus nuclear mass, right? In a delta M you have minus nuclear mass, ZMP plus NMN minus nuclear mass. So from here, if you bring that nuclear mass on the left hand side, and if you cube binding energy per C square on the right hand side, you will exactly get this. No?
Yes, sir.
Okay. And similarly, I can write M2. That will be how much? 20 MP plus 20 Mn minus binding energy per C square. ठीक है ना? Now, what I'll do, here there's an interesting fact. Suppose I'm multiplying by a factor 10. Then I have to divide by 10. No problem, right? Can I do that?
Yes, sir.
Sorry, not 10 or not 10. Please, not 10, not 10. So I can do 20. I can do both also, but I have to take 20 to understand that. Now this thing, what I can write, you see clearly. I can write like, here is the interesting thing. I can write this like, you have a 20 by C square and binding energy per nucleon or nucleus.
Screen blur है.
Is it? थोड़ा adjust कर लो please, because I didn't bring my system today. I'm using office office system. No, there's a problem. Only few minutes are there. Please adjust it. एकदम दिखाई नहीं दे रहा है.
मतलब बीच में नहीं दिखाई दे रहा था ये
अभी
दिख रहा है,
दिखाई दे रहा है ना? So you understood this part, that I can write like 20 by c square when I'm multiplying and dividing by 20. So binding energy by 20, that is representing actually total binding energy per nucleon of neon, because neon का mass number कितना है? 20, right?
Yes.
So binding energy by divided by 20 representing the binding energy per nucleon of neon. And same thing here I can do also. What I'll do for calcium, I'll do 40 by c square, and then you have binding energy per nucleon of calcium. Then what I'll do, I'll multiply this M1 by 2. So this will become 20. This will become 20, and this will become what? 40. When I'm multiplying both sides by 2, it will become 20, it will become 20, and this will become 40. Now rest of the play will depends upon this. Tell me which one will be the bigger. So you have a M2 like 20 MP plus 20 Mn, same. 20 MP, 20 Mn. 40 by c square, same. But here you have a game. अब बताओ किसका बाइंडिंग एनर्जी पर न्यूक्लियन ज्यादा है?
कैल्शियम का.
बाइंडिंग एनर्जी पर न्यूक्लियन कैल्शियम का ज्यादा है, राइट? कैल्शियम का.
Yes.
So this factor will be large. इसका मतलब there will be more subtraction. There will be more subtraction, because binding energy is some positive value, right? And this positive value is large, and you have already minus sign. So there will be more subtraction here. It means M2 will be smaller than
2m1.
exactly. So correct option will be what? D, right? Is this clear to all? Tell me if you have
Yes.
any doubt.
एक नंबर से हमने ये किया ना, गैस किया कैल्शियम का एटॉमिक नंबर ज्यादा है.
हाँ, we have already learned this, right? Up to 56, there is no problem with binding energy. There's a increment, right? Up to 56 iron, right? From 1 mass number to 56 mass number, there's an increment of binding energy, right? We have predicted this from binding energy per nucleon per. But in exam, definitely will get this kind of problem. There is some tricky, and that you have to guess. Is this clear? Okay, please do another problem and be careful about this. Another problem we have. So you have a mass I'm writing. I have to take help of note, because remember that mass, you have a mass. Nuclear mass is given. Nuclear mass of calcium given, calcium 2042, and that is given as 41.9586 22 atomic mass unit. Yeah, you means what? Atomic mass unit. Then this is also provided 20 40 on. इसका जो nuclear mass है, that is given as 40.962278. Okay, I have to take that help because I can't remember this. And then you have like potassium 1940 on. Okay, and that is given as 40.961825. 40.96 on 825 atomic mass units. Here all U means atomic mass units. 96 on 8, and then you have 962278, 96 on 825, right? Then 958622. Okay, good. And then you have nuclear mass, mass of a neutron is given. कितना होती है? 1.00866 U. And mass of a proton, that is also given. 1.00727 U. This is the mass given. And then you have to write the problem, part A. To write the problem, part A, find the energy required. Find the energy required. Find the energy required to remove a neutron. Find the energy required to remove a neutron. Find the energy required to remove a neutron. Remove a neutron from calcium 2042. Find the energy required to remove a neutron from calcium 2042. So part B, find the energy required to remove. Find the energy required to remove the proton from calcium 2042. Okay. So I'm doing this. Please follow the step and tell me if you have any doubt. आप लोगों ने लिख लिया problem? Have you written this?
Yes, sir. Yes, sir.
Shall I erase this part?
Yes.
Okay. Thank you.
Yes, sir.
Thank you.
फिर डी में प्रोटॉन निकालना सर.
In the second part, you have to find the energy required to remove a proton from calcium 2042. Now, first I'll write the nuclear reaction. In the part A, so you have a calcium 2042. So if you remove a neutron, what will be the product? It will have calcium 2041, right? And you will have a neutron. This will be the nuclear reaction when you are removing a neutron. So your mass number will be reduced to 1, and this will be the exact reaction. And you know the mass of this fellow. You know the mass of this fellow. You know the mass of this fellow. So first, to calculate the energy required, first you have to calculate delta M, and delta M is defined as mass of reactant minus mass of product. So delta M will be how much? ये कितना है आपका? कितना given है? Tell me that number I'm writing. 41.958 622, right? And product में क्या है? Calcium 40.96, and then we'll have 2278, right? And then we'll have reactant minus product, and product you have 41 with neutron, and neutron का कितना होती है? 1.00866 U. And if you calculate this number, you will get basically yes, it will be minus 0.0 on 2, 0.0 on 2, 3 on 6, 3 on 6 U. 0.0 on 2, 3 on 6 U. So this will be the first for any this kind of reaction. First you have to calculate the delta M, that is defined as mass of reactant minus mass of product. Then you know binding energy, and that is nothing but delta M into C square. and delta M you have calculated, and that is nothing but 0.0123 on 6. And from U to MEB, how will convert? Just you have to multiply it by 931.5 by C square, right? And of course there will be MEB here, and you have another C square is there, right? This C square. This will be cancelled, and you will get the binding energy, and that will be minus 11.47 mega electron volt. So if you remember, when you are calculating the binding energy हम कैसे calculate करते हैं? एक तो process ये है कि भाई आपका binding energy of the product. So this is the net binding energy of that reaction. So in general हम binding energy कैसे calculate करते हैं? Binding energy of the product minus binding energy of reactant of any nuclear reaction. ठीक है? अगर binding energy of product is greater than binding energy of reactant होती है तो फिर process को क्या बोला जाता है? Tell me anyone. If you have binding energy of product is greater than binding energy of reactant, then what will happen? Yesterday we discussed, right? There will be release of energy, right?
Exothermic process.
Exactly, exothermic process, or there will be release of energy. But another process to calculate the binding energy of that reaction is like by delta M, and that is defined as mass of reactant minus mass of product. So when you are calculating the binding energy for this reaction, if you are getting that this value, इसका मतलब क्या है? Binding energy of product is smaller than reactant. So you have to remove this. When you are getting binding energy of the reaction negative, it means to remove this, you have to supply this much energy. When you have a binding energy of the reaction is positive, there will be release of energy. When the binding energy of the reaction is negative, you have to supply this much energy to remove this fellow. So remember, binding energy calculate reaction का calculate करने का दो process है. एक तो product का binding energy minus reactant का binding energy. दूसरा process product का mass minus reactant का mass minus product का mass. यही binding energy calculate करने का दूसरा process है कोई reaction का. So if you are getting this binding energy positive, it means there will be release of energy. If there is a negative sign, it means you have to supply this much energy to remove this fellow. Is this clear what I am saying? Please tell me, then I can proceed now.
Yes, sir.
Yes, sir.
Okay. Now, if you remove a proton in the second part, what will happen? So this will be no longer be calcium, rather it will have potassium 1941, and you'll have proton, right? You'll have proton. And again, you have to calculate. You have to follow that same step. Mass of reactant minus mass of product. Now this time you will have potassium mass, right? So in second case, we'll have proton here. So no longer it will be potassium, calcium, it will be potassium. 19 plus 1, that will be 20, and 1 plus 41, 42. The mass number and atomic number is conserved, right? This is the exact reaction in the second part. Now if you calculate delta M, mass of reactant minus mass of product, and if you calculate binding energy, then कितना आ जाएगी आपका? I am doing it, please. I mean writing it. Please do it because already time over. Delta MC square. If you calculate it, you will get number that is I'm writing. Yesterday I'll ask you. 9.75 mega electron volt. But आपने क्या देखा? कोई आपका कैल्शियम है वहां से प्रोटॉन रिमूव करने के लिए कितना एनर्जी चाहिए? कितना चाहिए? If you have a proton, if you are removing proton from the system, you have to supply this much energy. और न्यूट्रॉन के लिए कितना चाहिए? न्यूट्रॉन के लिए कितना चाहिए था? हाँ, तो प्रोटॉन के लिए क्यों कम है? प्रोटॉन के लिए क्यों कम है?
रिपल्शन होता है प्रोटॉन.
Exactly, proton is having lower binding energy inside nucleus as compared to neutron. Proton के पास एक repulsive force हमेशा है. You have to keep in mind, okay? So proton is having lower binding energy in the nucleus because of repulsive force. Okay, I should stop here. Okay, हाँ जी.
सर बट जब हमने बाइंडिंग एनर्जी का कॉन्सेप्ट किया था तब हमने बाइंडिंग एनर्जी पर न्यूक्लियन किया ना.
Average.
ओके एवरेज. ठीक है सर.
Okay, stop.
Okay, sir.